All right, let's quickly do the example on page 123, example 14. And here's what it says. It's going to deal with geosynchronous orbits. And if you have, any of you have satellite TV, then you deal with this all the time. Because there's a satellite beaming the television signal down to us, and it's in a geosynchronous orbit, which means that it's always in the same place in the sky. It says a geosynchronous satellite is one that stays above the same point on the Earth, which is possible only if it is above a point on the equator. So all of these are launched into equatorial orbits. Such satellites are used for TV, radio, transmission, weather forecasting, communication relays. We want to determine the height above the Earth's surface, such as the satellite must orbit, and B, what is the satellite's speed, and compare that to a satellite orbiting at a low Earth orbit of a height of 200 kilometers. So I don't know if I'm going to have a chance to get to B and C, but I'm going to at least get A done. Well, let's zoom back out. Now the book is wrong, a little bit. The book is just a little bit wrong in how it solved it. So I thought I would resolve it for you using the correct idea. Well, we want to know what the radius of the orbit is, but we know from circular orbits that the period squared is equal to the 4 pi squared divided by the gravitational constant divided by the mass of the Earth times r cubed. And what I want is I want to use the information to find r, because once I know r, I know that r is equal to the radius of the Earth plus my height above the Earth. So if I want to get h, I just need to get the radial orbit, the radius of the orbit, subtract from that the radius of the Earth, and that'll be my height above the Earth's surface. Right? So because I want this height above the surface. Well, this is a basic equation that you can use. This is Kepler's third law as determined by Newton and Cavendish and so on. Kepler just knew that t squared and r cubed were proportional. That is, if you divided them, you would get the same answer no matter what. But later on, Newton and Cavendish figured this out. Well, this allows us to solve for r. So r is equal to gm times the period squared divided by 4 pi squared, and then, but it was r cubed, so what do I have to do to both sides to get r all by itself? Take the cube root, which I'm going to write as, just put a bracket around, 1/3 power. Does that make sense to you guys? Because on my calculator, I'm going to go to the power of 0.33333333333, and I'll get the answer from that. Well, this tells me what to do. I know I need to figure out, well, I know G. I know the mass of the Earth. I think you know the period. And then if you use what the book did, the period is wrong. Let's figure out the period. The period is equal to what is called a sidereal day. That is the time it takes the Earth to rotate 360 degrees on its axis. Now you might think a regular solar day, the Earth would rotate 360 degrees on its axis. But it doesn't. It rotates 360.9 degrees. You need an extra, almost a full degree. Now, why do you think that is? Well, I'll show you. Because we only got 5 minutes left. Here's the sun. Okay. And here's the Earth. And I'm going to draw the Earth's orbit like this, and I'm going to exaggerate. So let's say you're on the Earth, you're looking down on the Earth, and this isn't drawn to scale. But you're on the equator, and it's noon, and you look straight up. And the sun, if you're sitting at the equator at noon, it'll be straight over your head. And so, now, if you wait how much time does it take before the sun is straight up over your head again? 24 hours. Okay? And but while the Earth is spinning on its axis, it's also moving in a circle around the sun. So suppose you're right here. Now, suppose one day later, put the Earth right over here. Now, it's not quite that big, but I'm exaggerating so you can see it clearly. Well, you were right here, so you wait until the Earth turns 360 degrees and look straight up, and you miss the sun. You have to let the Earth rotate a little bit more before the sun is straight up in the sky. And that's a solar day. The solar day is the time it takes for the sun to be at its highest peak to the sun to be at its highest peak in the sky. That's a solar day, and that's 24 hours. But a little bit less than that is the time it takes the Earth to rotate 360 degrees. And that's what you want your satellite to do. You want your satellite to rotate 360 degrees when the Earth rotates 360 degrees. Because if it was 24 hours, it would move a little bit in the sky. It would move about 1 degree, or slightly less than 1 degree, or 1/365th of 360 degrees, right? Because every day it's going to move. If you use 24 hours, it's going to move. If you waited 6 months, your satellite is going to be 180 degrees from where you're pointing your satellite dish. Every day it's going to move about 1 degree away from where it should be. So first 2 or 3 days, no big deal. But you wait a couple of weeks and now your satellite dish isn't pointed in the right direction anymore. So you have to use a sidereal day. Sidereal day is 23 hours, 56 minutes, and 4.1 seconds. How do I know? Because I asked Siri. All right. I looked it up. I Googled it. All right. Now, this turns out to be, and because we're running out of time, this turns out to be 86,164 seconds. Just take 23, multiply that by 3,600, then take 56 and divide that, multiply that by 60, and then add them together, and then add 4.1, and you get this. Okay? So it's easy to figure out how many seconds, 23 hours, 56 minutes, and 4.1 seconds is. Now I can plug that in here. So now I can say that my radius is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Hope you can see that. Times the mass of the Earth. Well, everybody knows it's 5.98 times 10 to the 24 kilograms. Times the period squared. Well, that's our 86,164 seconds. Square that. Divide all of this by 4 pi squared. And then what do you have to do? Thank you. Thank you. So now what do you have to do? You have to remember to raise this to the 1/3 power. So you can use to raise to the power, and then you can go 1 in parentheses 1 divided by 3, or I just go 0.33333 like a bunch of times, and I get my answer. And it's 4.22 times 10 to the 7 meters. Now that's my radial distance from the center to where my satellite is. It's a very high orbit, actually. So now I can figure out what the height is. I just need to take the 4.22 times 10 to the 7 meters and subtract from that the radius of the Earth, which is 6.37 times 10 to the 6 meters. And when you do that, and I've already done the calculations, you get 3.58 times 10 to the 7 meters. Now that's equal to 35.8 times 10 to the 6 meters. That's 35,800 kilometers. Okay, so that's about 5 times the Earth's radius, 5 times the Earth's radius above the surface. So 1, 2, 3, 4, 5. So on this scale, I should have drawn the satellite out here somewhere. So if you're at the geosynchronous orbit, the Earth looks like a big ball. You can see the whole thing in space. And that's where all our weather satellites are. Now, once you know what R is, you just say V equals GM over R, plug that in. And then I'll let you look at the book to figure out what those ratios are. Let me zoom all the way out. Look at the whole thing. That is all.